In this capsule, we'll look at another factor that stabilizes organic anions, and that is hybridization. So we have seen different concepts that help explain the relative stability of anions in previous videos. In this video, we'll introduce hybridization of the carbon, which eventually explains the stability, the relative stability of these three anions. So the differences that you see in these three examples is the number of carbons, the number of bonds the carbon containing carrying the negative charge has. So in this first one, you see that carbon has a single bond to another carbon. In the second one, the carbon has a double bond. In the third one, the carbon has a triple bond. The way carbon forms these bonds is explained by hybridization. So what is the origin for this concept of hybridization? How did this come up? So let's go back to the basics. I have already written this bit here. Carbon and nitrogen, just to compare, I have a couple of elements here next to each other in the same row. Atomic number 6, carbon, atomic number 7, nitrogen. So the electron configuration of carbon and nitrogen, and its simplest terms is, we can write it like this. You are already aware of this from my previous class. So the electronic configuration of carbon can be written like that, but it's not entirely correct, because there's something called the Hund's rule, which says that electrons in the p orbital we know is degenerate. It has three suborbitals, px, py, pz along the three axes. So Hund's rule says that electrons tend to occupy the orbitals singly before they pair. So since there are three orbitals, three p orbitals, px, py, pz, the first electron of these two electrons, the first electron goes into the 2px, and the second electron goes into the 2py. And 2pz doesn't have any electrons. I just showed 0. We don't need to show that too. So this is the more refined electronic configuration of carbon, which follows the Hund's rule. Similarly, we can write the electronic configuration of nitrogen. The simplest one is like that, which you are already familiar with from a previous class, and the one in green is a better configuration because it follows the Hund's rule. Now, so we know carbon forms 4 bonds. Okay? Carbon forms 4 bonds. For example, the simplest one, CH4. Another one, CH3, connected to another CH3. Like this carbon is connected to 3 hydrogens, 1 carbon, so 4 bonds. So every carbon forms 4 bonds in a neutral carbon. Okay. So how do we explain that? So right now, in the refined electronic configuration of carbon, we notice that there are 2 unpaired electrons. For nitrogen, there are 3 unpaired electrons. So for nitrogen, it's easy to explain how nitrogen forms a compound like this, NH3. There are 3 unpaired electrons, and each unpaired electron is pairing up with 1 electron from the hydrogen, from each hydrogen, forming NH3. It's nice, simple, but what about the carbon? Carbon has only 2 unpaired electrons. So that's the point when people realized, oh, okay, so something is happening here with respect to carbon. How can carbon get 4 unpaired electrons, starting with this refined electronic configuration of carbon? So now, any reaction involves heating, chemicals, combining them. So there's some energy being input into the elements or compounds. So that energy can excite one of the 2s electrons, the 2 electrons in the second shell s orbital, to the available pz orbital, which right now has 0 electrons, but when the carbon gets excited, the 2s electron jumps into the pz orbital, 2pz orbital. So now we call this the excited state electronic configuration of carbon. So this is the excited state electronic configuration of carbon, and the one in green is the ground state electronic configuration. There's no energy, so it's there, but energy supplied, one of the 2s electrons jumps into the available 2p, and now you suddenly see carbon has 4 unpaired electrons. 4 unpaired electrons. So yeah, the 4 unpaired electrons of carbon can, for example, combine with 4 electrons from 4 different hydrogen atoms to make CH4. Okay, so the excited state electronic configuration explains the fact that carbon can form 4 bonds. Fine. Okay, but there's still something missing here, because what is missing is, if you look at this, there are 4 unpaired electrons, yeah, fine, but notice 3 of them on the p orbital and 1 is in the s orbital, second shell s orbital, second shell p orbitals, yeah, but so we know that the electrons in the p orbitals have the same energy, a little bit further off from the nucleus. The 2s orbital is a bit closer to the nucleus and has a different energy. So that, if we just look at this picture right now, that maybe gives us a picture like this. Let's say the bonds in blue, the 3 carbon hydrogen bonds I'm showing you there are in blue, and let's say they are from the px, py, pz electrons forming a bond with hydrogen atom, but then there's one with the fourth one with the electron in the s orbital. Just going by this particular configuration, excited state electronic configuration, we expect that 3 of the bonds of carbon will have similar bond length, similar bond strength, but one of them will be different. That's what we expect going by this electronic configuration. But in fact, it's not so, which is proved experimentally. All 4 bonds, all 4 carbon hydrogen bonds are of equal length and equal strength. So how do we explain that? So let me erase this entire thing now. So that's where the concept of hybridization is put forward. So what it says is the 4 electrons, the 1s2 is a core shell, so that doesn't participate in the bonding, but the 4 electrons, unpaired electrons in the sp, s and the 3p orbitals hybridize. So what you see in the textbooks is a picture like this. This is the energy of the electrons of the shells. Let's say the 2s shell is there, and there's 1 electron in the 2s orbital, that one, and then there are 3 other electrons in the 2p, which are slightly higher in energy, the 2px, py, pz, 2s, 2px, 2py, 2pz, and there's 1 electron in each. So we start with this. What is put forward is, yeah, these 4 orbitals hybridize, combine, and form what is called hybrid orbitals. With this process that forms the hybrid orbitals is hybridization. So since the 2s plus 3 2p orbitals are combining. So 1 2s and 3 2p orbitals are combining. You get 4 hybrid orbitals, and all of them will have the same energy. So this concept of hybridization is put forward to explain what is observed, that all 4 bonds in methane, like carbon hydrogen bonds, all 4 of them have identical bond length, identical bond strength, which suggests that there is no energy discrepancy. So this thing is put forward, hybridize to form 4 sp3 hybrid orbitals. So notice this term here, this is coming for the 2s, and since 3 p orbitals are involved, call it sp3 hybrid orbitals. So 4 sp3 hybrid orbitals are formed, all of them will have the same energy, and that energy will be somewhere in between the s and the p orbital energy. So maybe we say between these two, so maybe we'll just write 4 hybrid orbitals, 4 sp3 hybrid orbitals. Okay. So now all electrons will have the same energy, which is in between the 2s and 2p. Now, at this point, carbon hybridized to form, the sp3 hybrid orbitals, 4 of them, and now the sp3 hybrid orbital is used to form bonds with the 4. If we just take this simple example, so carbon is there, the hybrid orbitals of carbon are shown like this. On one side you have a larger lobe, on the other side you have a smaller lobe. And how did they form? They formed from, this orbital is like this, and then the p orbital is like this. So hybridization is happening, right? In that process they say, oh, the sp3 hybrid orbital looks like this, and in that process you see there's more area on one side, so the bond is much more strengthened. So you have, and then this is combined, so this is sp3 hybrid orbital of carbon, that's how it's depicted, and then there's the 1s orbital of hydrogen. This is sp3 orbital of carbon, they form a bond. So now you have the carbon-hydrogen bond and 4 such things, and all of them will have same bond length, same bond strength. Okay. So this is the sp3 hybrid orbitals. We'll do one more example and then stop this video. Okay. Now let's look at the next alkane. Methane is an alkane. The next higher alkane is CH3. So again, each carbon is forming 4 bonds. So now we saw the sp3 hybrid orbitals forming. So each carbon hybridizes, forms 4 sp3 hybrid orbitals, and then each carbon uses, let's say, this is the sp3 hybrid orbital of the first carbon. Let me just draw that a bit. So this is the sp3 hybrid orbital of that carbon, the first carbon, let's say on the left one, and then on the right carbon will also have its own sp3 hybrid orbital. So it's forming the carbon-carbon bond. So carbon, so it has a carbon-carbon bond, and then each carbon has 3 sp3 hybrid orbitals, and they are forming single bonds with 3 hydrogens. So you have the next alkane, ethane. So alkanes, as you know, we talked about that in previous videos. Alkanes are compounds, organic compounds that have carbon-carbon single bonds. So this is the simplest one is methane, the next one is ethane, and then propane, which is like this, CH3, CH2, CH3, that's propane. But you see the carbons, the 3 carbons here, each carbon is sp3 hybridized, and the bond between the carbon and hydrogen involves, in this example here, the bond between the carbon and hydrogen. This one involves the sp3 hybrid orbital of the carbon and the 1s orbital of the hydrogen. So in this short capsule we have seen why carbon hybridizes, the concept of why the concept of hybridization is put forward, and then we why is any theory put forward to explain certain experimental facts, so that hybridization explained the fact that all 4 carbon hydrogen bonds in methane are identical. So that's then expanded to other alkanes. So therefore you have this. So alkanes are compounds that have carbon-carbon single bonds in which carbon is sp3 hybridized. In the next video, we'll look at sp2 and sp hybridizations of the carbon. Carbon is versatile, it's flexible. So in the next video, we'll take a look at that. Stop now.